Right now, as we're watching this, the concentration of CO2 in the atmosphere has exceeded 420 parts per million, more than 50% higher than pre-industrial levels, and the single largest driver of global warming. The numbers are staggering. According to the IPCC, the global average temperature has already risen between 0.8 and 1 degree Celsius, and there is scientific consensus on the need to limit this increase to 2 degrees Celsius by the year 2100. In this chapter, we're reviewing direct air capture. Going from the problem up to business or market, we are making our pathway to net zero. Direct air capture is a technology that pulls CO2 directly out of the open air, actively removing the CO2 that is already there, complementing other technologies that focus on capturing CO2 at the source of emission. The International Energy Agency Net Zero by 2050 report made this clear. In every evaluated pathway to net zero, direct air capture is not optional. It is essential. The technology exists. The question is whether it can be made affordable enough to deploy scale. So where does Paraguay fit in this picture? Paraguay has built a legal foundation for climate action. The country has the International Climate Agreements under Law 251, enacted the Air Quality Law 5211, and in 2023 passed the Law 7190, the Carbon Credits Law, creating a national framework to generate, register, and trade carbon credits in line with international markets. The legal architecture is there. What Paraguay needs now is the technology to back it up. And Paraguay has shown itself serious. Even if Paraguay is not a major emitter, contributing only to just 0.06% of global GHG emissions, according to the models, between 2090 and 2021, the country achieved a 42.5% reduction in its greenhouse gas emissions, a remarkable result for a developing nation. Here is when the story gets interesting. Paraguay is a growing rice producer. In the last decade, planted area increased by 75%, and production volume by 70%. In the 2023-2024 season alone, Paraguay produced approximately 940,000 tons of rice, and for every ton of rice, there's a byproduct that nobody talks about: the rice husk, the outer shell of the grain. Rice husk represents around 20% of paddy rice weight. That means Paraguay generates roughly 188,000 tons of rice husk waste every year. This waste is extremely difficult to manage. Its high silica content makes it nearly indigestible for soil organisms. It doesn't decompose. When dumped near waterways, it contaminates aquatic ecosystem, and when it burned, it releases CO2, carbon monoxide, nitrogen oxides, and fine particulate matter directly into the air. Paraguay has a waste problem and a CO2 problem. Our team found that they have the same solution.
What if the answer to one of the world's biggest problems was sitting in a pile of agricultural waste? That's not a rhetorical question. That's our project, and we call it Panambi. Panambi is a word for butterfly in Guarani, the second official language of Paraguay. We chose that name because a butterfly does something remarkable. It takes a raw, abundant, and overlooked material and transforms it completely into something with purpose. That is exactly what Panambi does. We take rice husk, an agricultural waste from local rice mills, material that would otherwise be burned or discarded, and we transform it, step by step, into a high-performance CO2 sorbent. That sorbent is called 50BI-BT100, a bimodal silica support synthesized entirely from rice husk ash, and functionalized with 50% of branch PEI. The amine groups react selectively and reversibly with CO2, even at the ultra-low concentrations found in ambient air. But more on that later, because right now what I want you to see is where this material comes from. So let me walk you through our synthesis process. First, we obtain the rice husk ash through controlled calcination. Then we purify it to maximize silica concentration. From that purified ash, we synthesize our bimodal support using chitosan as a natural pore template. We then functionalize that support by wet impregnation with PEI, And finally, we granulate the powder into pellets, so the sorbent is physically ready for the cube. Speaking of the cube, let me show you the Pan & B cube. The external structure is a frame built from PVC pipes with acrylic panels. We chose these materials because they are inexpensive, lightweight, mechanically robust, and easy to assemble, keeping our capital cost well within our budget, while meeting every structural requirement of the competition. Inside the cube, the absorption bed is a horizontal back bed housed in a 2-inch PVC tube, 7 cm in length. Ambient air is drawn through the sorbent bed by an axial fan mounted downstream, in a suction configuration. This is a deliberate design choice. The air contacts the sorbent before it reaches the fan, ensuring it enters at true ambient temperature. So, in summary, RHA, ketosene, PEI, and a 1 cubic foot PVC cube. Simple materials, deliberate engineering, and a sorbent designed from the ground up to capture CO2 from the air we breathe. But engineering without numbers is just a story. So let's take a look at numbers.
In this section, I'm going to be talking about some preliminary calculations. As air flows through the packed sorbent bed, it loses pressure due to friction with the particles. This is called pressure drop. The magnitude of this pressure drop depends on particle size, bed length, void fraction, and airflow velocity, and can be precisely calculated using the Ergun equation, which applies to packed beds. As shown here, our calculated pressure drop for a flow of 20 standard cubic feet per hour is only 0.0013 pounds per square inch gauge, which is way below the safety limit of 1, meaning any standard 12 volts DC fan can easily handle this airflow. We can also see in this next graph that the power required is also very low. The negligible pressure drop is directly linked to our particle size. By granulating the sorbent into pellets of 1 to 3 millimeters, we ensure that the air flows freely through the bed with minimal resistance. To calculate the capturable CO2, we need to first establish 3 things. First, the total CO2 inlet. We do this with the airflow, the CO2 concentration in the air, and the total runtime. And it gives us a total of 71.3 milligrams of CO2. Then we verify the sorbent absorption capacity, which we don't have direct data to our specific sorbent and conditions, so we extrapolate from various sources and get an absorption capacity of 50 milligrams of CO2 per gram of sorbent. Multiplying this number by the total sorbent in the packed bed, we get the maximum capacity that is more than 4,000 milligrams. As we see, this capacity is way above the total inlet, so the sorbent capacity is not a limiting factor. The sorbent will not saturate. And the last thing is the efficiency of our sorbent. We considered an efficiency of 60% based on Takar, who measured absorption of CO2 with bay silica pellets at 420 ppm and 25 degrees Celsius using conventional unimodal silica. Our bimodal sorbent, which has been shown to outperform the unimodal one by 261% at an equivalent payloading, as reported by Witun, is expected to perform at least as well under these conditions. Finally, to get the CO2 that we expect to capture, we just have to multiply the total inlet of CO2 and the efficiency, and we get a number of 42.8 milligrams of CO2 in 10 minutes. These are the sources that we check to things for like sorbent capacity and efficiency.
Bimodal bay silicon dioxide from rice husk ash, a low-cost sorbent for direct air capture. For our ChemE cube, we selected a bimodal mesoporous silica support synthesized from rice husk ash, functionalized with bay, and structured using chitosan as a natural pore forming template. This absorbent system was designed to capture carbon dioxide directly from air at ambient concentration. The use of an agricultural waste as a raw material reinforces the sustainability of the process. global rice husk ash production exceeds 4.4 million tons per year, demonstrating the large-scale availability of this low-cost feedstock. Also, RHA produced under controlled calcination conditions contains 98 to 99% amorphous silicon dioxide, a purity comparable to commercial-grade fumed silica or tetraethyl orthosilicate, but at a fraction of the cost. The architecture that results from this synthesis is bimodal, meaning the support contains both mesopores and macropores. That combination is what separates our material from conventional unimodal absorbents. As shown in this figure, at high pay loadings, unimodal silica suffers from pore blockage, while bimodal silica maintains accessibility thanks to macropore diffusion pathways, leading to higher effective amine utilization. Therefore, pay impregnant into mesopores of the bimodal porous silica can effectively react with carbon dioxide. Bimodal supports dramatically outperform unimodal equivalents. For functionalization, we chose physical wet impregnation over covalent grafting. Physical wet impregnations enables higher pay loadings and more than doubles carbon dioxide capacity compared to grafted systems.
Safety is an important aspect in our design. It will be integrated into every phase of our solvent synthesis process. Let us walk you through the hazards we identified and the controls we put in. Phase 1 involves grinding and calcinating dry husk at high temperature in a muffled furnace. The primary risks here are inhalation of fine dust particles, thermal burns, and fire hazards from biomass combustion. Operators wear N95 masks, safety goggles, and thermal gloves at all times. The furnace is operated in a ventilated laboratory, with strict temperature monitoring and mechanical guards on all grinding equipment. Phase 2 involves acid leaching with dilute hydrochloric acid to remove minerals impurities. The risks here are more serious: chemical burns, exothermic reactions, and emission of acidic vapors. All acid handling is performed exclusively under a fume hood, with secondary containment in place at all times. Acid and base waste streams are kept strictly separate, and all liquid waste is neutralized before disposal. Phase 3 uses alkaline sodium hydroxide solution and hydrothermal aging at 100 degrees Celsius. The key risk in this phase is overpressure buildup during aging. All hydrothermal aging is carried out in open or pressure relief system, never sealed. Temperature is continuously monitored. Full PPE is mandatory, and calcination following drying is performed outside in the main container to avoid heat accumulation. Phase 4 is the most chemically sensitive step. We use ethanol as a solvent to impregnate the silica with branch PEI. Ethanol is flammable and PEI itself is chemical irritant. All impregnation work is carried out under a certified fume hood, using only explosion-safe electrical equipment. The solvent is evaporated in an open system, and the adsorbent is completely dry before it's ever placed inside the cube. No residual solvent enters the cube. Phase 5 is granulation, converting the powder into pellets of 1 to 3 mm in diameter. This step is not optional. Without it, fine particles could escape into the airflow and damage the CO2 sensor. Inside the cube, our designs include a particle filter in the outer line, sized below the minimum particle diameter of our solvent. The adsorbent is physical contained at all times. No liquid, no acid residue, and no loose powder must exit the system during the operation.
Now I'm gonna be talking about our budget. Our total budget is under $500 because we rely on simple materials and existing lab equipment. A key advantage is our raw material. rice husk is an agricultural residue with near zero cost, which significantly reduces overall expenses. In addition, we use PVC for the absorption column, which is inexpensive, widely available, and easy to work with. Most components such as fittings and tubing are also low cost and standard, meaning no specialized infrastructure is required. Since all the synthesis steps are carried out in university laboratories, we avoid any additional capital investment. Overall, this makes our system not only cost effective but also scalable and accessible for broader implementation.
This report evaluates the market potential and economic feasibility of a CO2 capture system. It focuses on key aspects such as market size, target customers, competitive advantage, and scalability. The DAC, direct air capture market, is rapidly growing due to the global climate policies. It is expected to spend from around 62 million in 2023 to over 1,727 million by 2030. High carbon credit prices and a strong investment reveal a significant amount demand. The main target is Paraguayan agro-industrial companies exporting to the European Union, especially in rice sector. These companies must comply with environment regulations like CBAM. Secondary customers include governments and companies aiming to offset emissions. The system uses rice husk as a low-cost raw material to capture CO2. This reduces the production costs, enables cheaper regeneration, and promotes a circular economy by reusing industrial waste. Compared to the existing technologies, the proposed system is more affordable and sustainable. It uses local materials, reduces the dependencies on imports, and offers scalability through modular design. The system can generate revenue through carbon credits, showing promising economic potential. Also, reduces costs by using waste materials instead of expensive inputs. It offers an accessible and sustainable solution for CO2 capture, especially in developing markets.
You are probably already seeing an origin of our cube's design, but you are probably still wondering what is the most innovative feature. Well, that will be our adsorbent. It's made from rice husk, a byproduct that Paraguay generates in massive quantities and that currently ends on being burned in boils. We take that waste, convert it into high purity ash, and through a synthesis process that we control from start to finish, we produce a material with a real capacity of capture CO2. We don't buy that solvent, we manufacture it. That means total control over the production chains, cost radically lower than any synthetic alternative and raw material that Paraguay already produces in abundance. But what makes this project particularly valuable is just the cost. It's the way it closes the loop. The same industrial sector that generates emissions is the one that produces the waste, which in our hands become the solution. There is something almost poetic about all that, and also something very concrete, a circular economy model. The material we synthesize is not a niche laboratory product. Scientific evidence supports its potential for industrial scales applications. We are talking about a competitive adsorbent produced from local waste, using a process that can be replaced and scaled out with the country. Our cube is not just technology, it's a model in which Paraguay ceases to be a bystander to the climate crisis and instead offers a solution originating from Paraguayan countrysides to a challenge that belongs the entire world.